Good morning, everyone. This will be a question and answer session. So the purpose is you can ask questions about anything related to 218, and I will answer them. You can ask questions when I ask for them. Either you can put them in the chat, you can do that now or later. You can also unmute your mic and ask the questions over the microphone. So there was already a question asked. This question is about exercise 6.2.1d. The question is to compute the triple integral over the region E of the function 2yz dv. The region E is, so this is given in the question, this is given as the region bounded by 5 planes, namely these five planes given by these equations. So x plus z is 2, z minus x is 2, z is 1, y is minus 2, and y is 2. So the first thing we want to do in such an exercise is always, can I have some suggestions? How should we start in the exercise? What should we do first? Very good. We want to draw the region, so multiple people sketch, draw the region. That is always the first thing that we want to do because we need to know how it looks like so we can set up the integral correctly. Okay, so the first thing I'm noticing here is that there's two, let's see, these are vertical planes, y is minus 2 and y is 2, and that's the only planes that involve y. So if I were to draw this in a 3D picture, I can already see, well, let's do them in red, right? So let's draw the red planes. Well, y is minus 2, that's going to be over here. So it's going to be a plane like this. And y is 2. So this is minus 2, this is 2. It's going to be a plane like this. So what's happening here is that these other planes, they have no y involved. So they're going to be somewhere in between of those things, in between those two planes, these two vertical planes. So because it's a little bit more convenient, I'm going to sketch the other three planes. Let me do that in blue. I will sketch them just in the XZ plane. So we'll forget about y because y plays no role, right? I will get the same picture for every y. So I'm gonna just sketch them in the XZ plane. Let's do that over here. So this is one way of doing it. Of course, you can also sketch all these planes just directly in the three-dimensional picture, but I think in this case it's most convenient to sketch them in the two-dimensional picture because it's much easier to sketch a 2D picture than a 3D picture. And then later on we can put it in the three-dimensional picture if we want. Okay, so let's sketch all these three equations. Well, z is 1, that's just a line, right? So z is 1, that's over here. Right, so this is z is 1. Then I have x plus z is 2. Well, let's write everything such that z is a function of x. So this is the same as saying that z is 2 minus x. And this is the same as saying that z is 2 plus x. So 2 minus x. I have 2 minus x going to go like this. 2 minus x. And 2 plus x will go like this. Right? And we need the region bounded by these three things. So that's going to be this triangle over here. Okay, let me ask, are there any questions so far about what I've done? Okay, I'm not done yet with the sketching in the 3 dimensions, but I've at least sketched this 2-dimensional part. Is there any question about that? Okay, I think everyone is fine. Please, if you're not sure, feel free to ask. Okay, so now you don't actually have to do this. I think it's convenient to draw this picture in 3 dimensions. So I've got this triangle over here, right? And this is true regardless of what y is. This is true for every y. So I'm going to get this picture for every y. So in other words, for instance, if y is 0, then I'm going to get this triangle over here. So it's going to look a little bit like this. Right? But this is now happening on the XZ plane, Johnny, because remember, I'm projecting on the XZ plane. So that's exactly what's going to happen. This will be the projection on the XZ plane. right? Because y plays no role here. So this is on the xz plane. So I've got my triangle over there. That's for y equals 0. But I've also got a triangle that corresponds to y equals 2, right? So this will be a triangle in this red plane over here. And I've got a triangle corresponding to y equals -2. So it's going to be a triangle like this. And now I see that, okay, what does it look like? Yeah, it's going to be this triangular region stretched out between the planes y is -2 and y is 2. So I think this is the most convenient way to do it. Of course, you can also draw just all the planes in 3D, and then you should arrive at the same answer. Okay, let me see if there are any other questions. So Nicole, did you also have a picture like this? You were the one who asked the question. Okay, it was similar. You said okay. So okay, let me just finish the idea of the question. Well, what should we do now? Well, we should make a triple integral, and we should see, well, y is between fixed numbers, so right. So for instance, we could choose y to be, yeah. So we see from the picture. Let's write this in red. That y is between -2 and 2. Then from the xz plane, we see that. Okay, so now we have to think about how do we parameterize x and z. To be honest, I don't know by head whether this is type 1, 2, or 3. But this is the type where the 5 variables between two fixed functions, but in this case the functions are constant. So this is y is between a lower function of x and z, which in this case is just the constant -2, and the upper function of x and z, which in this case is the constant +2. I don't know by head whether this is type 1, 2, or 3, but that's not that important, right? The important is about the method. So that are the bounds for y. Let me know if there are any further questions or whether this is clear or not. Okay, now then I need to think about x and z. So as you can see, this is the shadow in the xz plane. So this is the region D. So now I have to think, should I do this in type, yeah, so now in the xz plane, should I do this in type 1 or type 2? That's the question. Now let's do a little poll. So my blue region, should I do this in type 1 or type 2? So let me make a poll, multiple choice question. Blue region type 1 or 2. Okay, please answer the poll. Okay, so the majority of you have answered. Okay, so the thing is, how should we check whether we should do type 1 or 2? So let me go to the answer. Well, if we do, let's say we would do type 1, right? In type 1, we say, well, the x variable is between. Oh, I'm lagging a little bit. Please let me know if the audio was unclear. I am type 1 is vertical slices, so I'm between these two. So that means I've got a lower function. Let's do that in purple. So the lower function will be this. Ouch, I'm lagging. Well, I hope you can all still hear me. And the upper function, let's do this in orange, will be this, right? That's going to happen if we do vertical slices. We go from the bottom function, which is the purple one, to the top function, which is the orange one. And we can already see a disadvantage because the bottom function is a nice and easy one, but the top function has to be split up into two parts, because on this region it will be, the behavior will be 2 plus x, and here the behavior will be 2 minus x. Yes, I'm gonna have to split it up into two parts if I do it like this. However, if I do it in type 2, so then we take horizontal slices, so we can see that these are then the bounds. Yeah. Now the leftmost function, so now we go from left to right. Let's maybe do that in red. So the leftmost function is this red function, and the rightmost function is, do I have a color left? Yeah, gray. Is that function. And you see these are functions which are nice. They are, how should I say that? They are defined by a single curve. So I'm not gonna have to split it up. So I think here it's most convenient to do it as type 2. Okay, let's continue in blue, because this is all about the blue region. So in type 2, we see that z is between 1 and 2. What about x? Well, that's between the red curve. Well, let's do that in red. So the red curve is, this is the curve where z is equal to 2 plus x. So x is going to be equal to 2 minus z. And the upper bound, that's the gray region. So let's do that in gray. That's where z is 2 minus x, so x is 2 minus z. Oh, I made a mistake for the red region. 2. Z should have been z minus 2, apologies. Yeah, I rewrite this equation. I made a sign error. So so I take this equation, z is 2 minus x, and then I rewrite in terms of x. So x will be z minus 2. So z minus 2. Z minus 2. Z minus 2, not x. Okay, any questions about this type 2, about type 2 split of this part? Okay, then I can, yeah, for the inner integral, so for let's start with the inner integral in y. So we have 2yz dy, and then let's say we have dx dz, right? Because z is the constant. So y is from minus 2 to 2, x is from z minus 2 to, sorry, z minus 2 to 2 minus z, and z is from 1 to 2. So I think this is the correct answer. So are there any questions? And I will not write this out because this is very easy to compute, yeah? So are there any questions? And does this answer your question, Nicole? Yes, thank you. Okay. Hopefully it's clear. I see that there are no questions in the chat, and then I will go to the next question, which is exercise 6.3, number 6b. So I'm gonna clear the screen in a second. So let me know if there are any further questions about this. Okay, let's clear the screen, and let's continue with 6.36b, which is need to evaluate the triple integral of the function z. So we have a region inside the sphere x squared plus y squared plus z squared equals 1, and below the cone with equation z equals square root of x squared plus y squared. Below that cone. Oh yeah, of course, that makes sense. Apologies, I was a little bit confused when I looked at the solution in the course notes, but I see what my solution, where my confusion comes from. Okay, so how do I start again? Okay, I'm not gonna ask this again because this is always the case when we have a triple integral. We always start by sketching. Okay, now, yeah, there's no way to split it up into certain planes, so I should just make a 3D picture right away. Okay, so let's first start with the cone. How do I draw this? Okay, so this is, as you know from chapter 1, this is a circular cone going up. So let's say z equals 1, then we have a circle around here with radius 1, so like this, and then we go up from there. So yeah, so that's a circular cone going up. Then I also have a sphere. Maybe let's do that in a different color. So let's do that in red. So I've got a sphere of radius 1. So I've got a sphere of radius 1, and then going through there. So it's gonna go like this, and then like this. Okay, I've only drawn the top part. Now let's also draw the bottom part, right? Because that's also relevant for this question. Okay, again, my drawing is not great, but hopefully you see what's going on. I've got this cone going up and a sphere around the origin, and I'm looking everything inside the sphere, but it must be outside of the cone. Okay, any questions or remarks about my sketch? Sorry, this is y, this is x, and this is z. Okay, so there are a couple of things that we want to do. We need to first think what technique are we using. Well, we have a sphere, so again, and so it makes sense to use spherical coordinates. Sometimes you would use cylindrical coordinates, but there are no cylinders here, so that doesn't make sense. So spherical coordinates looks very good for this question because I have a sphere, okay, and then we have this cone, so we need to figure out how to do this. So let's do spherical coordinates. Of course, you have to know how these things are defined. So okay, so we have x is rho cos theta sine phi, y is rho sine phi sine theta sine phi, and z is rho cos phi. Yeah, and another important equation is that rho is the distance to the origin, so x squared plus y squared plus z squared is equal to rho squared. Yeah, I think these are the important equations of spherical coordinates. Olivia, did you try something, or did you get stuck somewhere, or did you just not know what to do, or do you have any particular questions, or should I just carry on? Please just carry on. Do we usually give constant planes? Well, that depends on the question. Okay, so now we need to determine the bounds. Okay, there's a couple of things we need to do, right? You don't understand the bounds. I think that's the most difficult part. So we have to do 3 things. Oh, let's write this down. Right, we need to rewrite integrand. Let's not take up too much space by this. We need to rewrite the integrand in terms of the spherical coordinates, We need to not forget about the Jacobian, and we need to find the bounds for the spherical coordinates. Okay, so the Jacobian, that's something, okay, this was covered in detail yesterday. So we'll just give this, I think it's rho squared sine phi. The integrand z, well, you can see that's rho cos phi, so that's not going to be an issue. The difficult part here is the bounds. So how do you determine bounds? Okay, so we should look at the picture here. And we should think about, okay, what do these variables represent, right? We have variables. Okay, let's give them a different name. So we have rho, we have theta, and we have phi. Okay, so what does the rho represent? As I already said, this is the distance to the origin. Now we can see that we're in this sphere, and we can see that for every ray that I take. So let's take a blue ray. So let's take a certain direction, right? The theta and the phi give a certain direction. I will elaborate on that a little bit more. And the rho then gives me the distance. But if I go in a certain direction, let's say I go in this direction, well, at some point I'm going to hit the boundary. And the boundary is where rho equals 1, because that's x squared plus y squared plus z squared. Yeah? So here we have that rho equals 1. And at the origin, we have that rho equals 0. So we see that no matter which direction we go to, we always have that rho is between 0 and 1. And you can see, because this cone going upwards also has goes upwards only in certain directions. So we're never going to hit this cone when we go in a certain ray. Because we can either go through the cone, but that means in that direction we simply have we have nothing. So this should be dealt with the direction, which is given by theta and phi. Okay, I'm not sure if that is clear. So maybe before asking questions, let me first explain how to get the bounds for theta and phi. Okay, so theta, that's the angle on the xy plane. So that's going to be this angle over here. This is the angle theta, right? That's the angle between the xy plane. So it's important that you know what all these variables represent. So theta is the angle on the xy plane. Now we can see in the picture, right, that we go all the way around because we are inside the sphere and below the cone. That certainly includes the red circle on the xy plane, and it goes all the way around. So theta certainly is from 0 to 2 pi. Yeah, so we can see from the picture that theta is from 0 to 2 pi because we take a whole circle, we go everywhere, in every direction we go like that. Okay, now comes the difficult part. Okay, let me ask if there are questions about theta. Do you guys all agree with me that theta is from 0 to 2 pi because we going in all those directions? Yes. Okay, I've got some yeses, thank you. Okay, now about the phi. What does phi represent? Remember, phi represents the angle with the positive z-axis. So phi, so there will be an angle like this. So this angle, sorry, it's over there. So this angle phi, yeah. If phi is 0, then we are on the positive z-axis. If phi is pi, then we're on the negative z-axis. If phi is pi over 2, we're on the xy plane. So that is what phi determines. It determines the angle with the positive z-axis. Okay, and now we see, do you mind drawing a different color around region E? Maybe I should do that, yeah, maybe that's a good idea. What color? Let's do purple. Okay, so what is the region E? Okay, so it's everything not in the cone. So what do we have here? We have got a purple circle around here, and then we've got our sphere. I will just draw the boundary there. So in purple, I've tried to sketch the boundary of the cone, and then it's everything outside of the cone, right? It's below the cone. So it's everything in the red circle, which is below the cone. So it's everything outside of the cone, but inside of the sphere. Hopefully, is that clear, or would you like me to explain a bit more? Okay, that's okay. Well, that is actually a good question, because that's what we're going to have to use now. Because now we see that, well, if our angle phi, for instance, is 0, so if we go to the positive z-axis, then we're inside of the cone. And in that case, we're not in the region, right? So phi is 0 is certainly not included. And if phi is small, then we're still inside of the cone. So you see, at some point, we're going to go outside of the cone. So a bunch of phi's here are all not included, but at some point phi is included again. And from then on, all the angles below there is going to be included. And that is in any direction. So no matter what theta is, theta determines, yeah, if it's, say, in this direction, it could be like this, it could be like this, right? That's determined by theta. Theta determines in which direction we angle our angle phi. Hopefully that makes sense. But every direction is the same. We in the beginning we will be inside of we'll be above the circular cone, and then at some point we will hit the boundary, and from then on we will be outside. We will be below the cone, and therefore we will be in the red ball or in the purple region. Yeah, so that's important. I see this from the picture. So let me ask if there are any questions about that. I'm not done yet. I just want to verify here the intuition that our phi starts off above the cone, but we want the region below the cone. So we need to find the angle phi for when we are actually outside of the cone, so that we are actually below the cone. Does phi move clockwise or anti-clockwise? So phi moves from here in any direction. For instance, in the ZY plane, it moves like this, and then it hits there. So I don't think we can speak about clockwise or anti-clockwise here, because in a different direction, if I go in the opposite direction, still in the ZY plane, it will move like this. Maybe I should draw some trajectories. You don't understand phi. Okay, that's clear. Let me draw some trajectories in gray. So in the XY plane, phi would go like this. Okay, so this is not an angle, but this is like a trajectory that's for a fixed radius. So if I fix my rho, say rho is 2, and I fix my theta, so in this case theta is pi over 2, then I'm going in that direction. So that means my phi will trace, if I vary my phi, I will trace this path over here. So that's for a fixed theta and for a fixed rho. Now if I take the same rho, but I take 3 pi over 2, that means I will go like this. Again, from the positive z-axis to the negative z-axis. Let's say that that theta is 0, that means I go in the zx plane, so I will go like this. And if theta is pi, then I will go also in the zx plane, but in the opposite direction, so I will go like this. Yes, so I'm starting on the positive z-axis, and I'm sort of going down all the way to the negative z-axis. This is for a fixed theta and for a fixed rho. I think this hopefully makes it clear what is. Is this clear what I've drawn, or are there any more questions? I don't know how to explain it better. So hopefully it is clear. So now we see, well, if we see, no, phi goes from 0 to pi, right? Because this is the angle 0 for phi, and this is the angle pi. So that's phi goes from 0 to pi, and this is pi over, so pi over 2, we will be in the xy plane, no matter what theta is. See, pi over 2, that's halfway, right? So phi is 0 corresponds with z positive, phi is pi corresponds with z negative, and phi is pi over 2 corresponds with z is 0, so then we're in the xy plane. Okay. So now we see what happens. At some point, we're going to hit this cone. So we need to figure out when do we hit this cone. And it doesn't matter in which direction, because the cone is circular, right? So it doesn't matter, we can go, doesn't matter what theta is, we will always hit the cone at some point. So let's compute this intersection point in the ZY plane, because that's a little bit easier. So let's just restrict to the ZY plane. So this is where x is 0, right? Well, there our red thing is a circle. So this is if I project if I just look at the xy plane, and our circular cone, right? So this is so this is where x is 0. So we have y squared plus z squared equals 1. So that's the red circle on the zy plane. Phi is in none of these planes. Phi goes through the entire three-dimensional region. But I'm only going to look at the zy plane. I will explain in a second. So let me just finish my picture. Okay, now let's look at the other equation. That's the circular cone. Yeah, let's do that in black because I did that in black before. So there we have that z is the absolute value of y, right? Okay, let me explain this. We have z is equal to the square root of y squared, which is the absolute value of y, right? Because x is 0 here. Yeah, so if you look at a three-dimensional picture, this is what you see if you take x is 0, right? I hope you all agree with me that this is the picture you get in the zy plane. Okay, I get one yes. That's good. Well, now, in this picture, we can also draw our angle phi. I think that's a good idea, so let's do that. Phi is the angle with the positive z-axis. So phi is this angle over here, phi. Right? Because that's how phi defined, the angle with the positive z-axis. And so we see that if you compute the intersection point, let's draw it in yellow. If we compute the intersection point, then we exactly get the angle phi from which we are right from 0. So in the yellow region, we see that's where phi is from 0 to whatever phi is on the intersection point. That's where we are above the cone, and then on the rest we will be below the cone. So we need to compute the intersection points. So let's compute the intersection points. Well, then we have that z is the absolute value of y, and we have that y squared plus z squared equals 1. Okay, so in other words, we have y squared plus the absolute value of y squared is 1. So 2y, but of course, absolute value of y squared is the same as y squared, so 2y squared is 1. So we have y squared is a half. So y is plus or minus the root of a half. So that's 1 over root 2. Yeah, and what's the z? Well, z will be the same. Well, yeah, z will be the absolute value of that. So now this the yellow point over there. So there will be another point on the other side, but I only need one. This will be 1 over root 2. And the z value will be the same. It will also be 1 over root 2. Okay, there's a question. Why isn't phi between pi over 4 and 3 pi over 4? Okay, I will answer that question in a second once I finish the rest of the question, okay? Please, I would like some confirmation. Do you guys understand how I computed my intersection point? And do you all agree that this is the intersection point where both y and z are equal? Okay, I get one yes. Can I have some more yeses that you all agree with me so far? Okay. Okay, well now I have to compute the angle. I actually see, since the y and the z coordinates are the same, this angle should be pi over 4, right? So let's do that in green. So that's the green angle. This angle should be pi over 4. Because it's half the angle from the z-axis to the y-axis. Actually, I could have not, it was not necessary for me to do all the computation. Because I know this line here, whoa, what happens? This line here is where z is equal to y, right? If y is positive. So this is the line where the angle is degree pi over 4, right? Because z equals y, so that's halfway. So I actually don't have to compute this, just showing you that you can actually compute this. You can find the point, and once you have the point, you can find the angle. You all know how to do that, hopefully. But if you just say, well, this is an angle of pi over 4, that's also fine, because it's clear from the picture, since z is equal to y, that this point must be where the angle is pi over 4. Okay, now let's go back to our 3D picture. So apparently, if phi is 0 up until pi over 4, this is where we're going to hit the boundary of the circular cone. And in the first region, as I explained before, we'll be above the cone. But once I'm below pi over 4, in all this region over here, so from pi over 4 all the way to pi, I will be below the cone. And that's the region that I need. Yeah, so I can see here from the picture that the phi is, the lower bound should be pi over 4. That's when I first hit my circular cone. And the upper bound should be pi, because that's going to be the negative z-axis, right? It's the whole region from there to there, and that's in every direction. So this is why the upper bound here is pi. I can simply see this from the picture, because that is the largest possible value for phi. And no matter, and if phi gets large, I will always be below the circular cone. Yeah, hopefully that answers your question about you, Olivia. Why not pi from 3 pi over 4? Well, 3 pi over 4 is somewhere in this direction, but I can go further, right? If I go further than 3 pi over 4, I will still be below the cone. I will always be below the cone once I traverse my boundary value of pi over 4, which I just computed over there. Yeah, is that clear to everyone as well? So please give me a yes in the chat if all of this makes sense. I get one yes. Yes. Not really. Can you explain which part is unclear? The phi part is not understandable. Yeah, okay, so you just need to have a good 3D view of what this angle phi is. It will be the angle with the positive z-axis. And since at some point I will hit my cone, how does it stop at pi? Well, this is where it's 0, and that is where it's pi. It's pi on the negative z-axis. So okay, let me explain the difference. Theta goes from 0 all the way around in a huge circle back to its origin. Back to 2 pi, which is then equal to the angle 0. For phi it's different, because theta already goes round. Phi only has to say how much are we going up, right? Because how much we're going in the xy direction is sort of determined by theta. Phi only says how much are we going up. Phi is 0 means we're going all straight up. Phi is pi means we're going straight down. And phi is pi over 2 means we're going in the xy plane. Could be any direction in the xy plane. So any of these directions in the xy plane. So 0, blah, 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 pi over 4, pi over 2, 3 pi over 4, negative z-axis, pi. And that's where it stops. And it's also in the other direction. So 0, pi over 4, pi over 2, 3 pi over 4. Hit the z-axis, pi. Okay, hopefully I think this is a little bit more clear. Okay, let me know if there are further questions. Okay, that's good. Good that you get it. Well, now I think... so now let me just do the triple integral. So we have everything is constant. So let's say theta is from 0 to 2 pi. Phi is from pi over 4 to pi. Rho is from 0 to 1. Z, that's equal to rho cos phi. Be careful not to forget the Jacobian, which is, I believe, rho squared sine phi. And then we have d rho, d phi, d theta. Can do different orders because none of the variables depend on each other. So that's okay. I'm not gonna compute this. You can do that yourself. But this is the integral. Yeah. So are there any final questions about this question? Okay. Well, if not, does anyone have another question? I think, well, this was long, but I think this was good because we now all understand how spherical coordinates work, or at least understand it better. Hopefully my pictures have made things more clear. I'm lagging a bit, which is annoying. Test. There, I see a lot of question marks. Can we please do another example if possible? Well, how did we get pi over 4? Yeah, I already discussed this in detail, so we need to... I'm lagging a little bit. Please let me know if the audio is breaking up. So I start at 0, and then I see that at some point I'm going to hit the boundary of the cone. And how do I determine when I hit the boundary of the cone? Well, I can see that it's going to be the same in every direction. Doesn't depend on theta. So let's take theta a fixed value, and for instance, then we could take the zy plane. Then I draw my zy plane picture. I compute the intersection point, or I see that here we have the line z equals y, and therefore the angle will be pi over 4. Okay, there's a question by Nicolo. How should I draw a surface z equals x squared in 3D? So you guys want another example? Well, you're gonna have to come up with another example while I answer Nicola's question. How to draw the surface z equals x squared? Okay, so this is a general question. How to draw it in... you can do it in the zy plane, you can do it in the zx plane, but it sort of depends on the question. Yeah, so let's see how to draw z is x squared in the 3D. Well, in 2D it will be easy, right? So let's do the z, let's write the zx plane. It will be like this. But now the question is, how do I draw this in 3D? X, y, sorry, y, x, z. So let me answer this question quickly. Well, we see that there's no y in here, right? So it doesn't matter what y is. For every value of y, I get the same thing. So for instance, for the value y is 0, I get a parabola like this, right? So I've drawn my 2D picture here. I've drawn it in 3D like that for the value y equals 0. But there's no y here, so it doesn't depend on y. So I could also take y is 1, and then I will get the same picture, or y is minus 1, I will get the same picture. You get the point, right? I get the same picture for every value of y. So what we get, yeah, someone explained it in the chat, a parabolic gutter running along the y-axis. I think that's a very good description. I like that a lot. Yeah, so what I would do when I have such an equation, I would say, oh, this doesn't depend on y, so let's first draw it in the zx plane. Could be more complicated than this. And then I say, okay, I can just draw one of them, and then it will repeat infinitely long along the y-axis, because it will the same. I will have the same picture for every y. Okay, is this clear, and does this answer your question? Yeah, okay, I think you said yes. Okay, so are there any other questions? I can recommend you the... Oh no, never mind. If you want me to do another example, you're gonna have to give me an example, and I will be happy to do it. Okay, I see two questions. Let me first answer the question. If the proofs that are asked in the exercise, will they be asked in the same way in the exam? That depends. Some of the proofs in the exercises are very difficult. We're not likely to ask them in a similar way. But they are good exercise. So if you can answer them the way that they are asked in the exercises. So if a proof is very difficult, then it's very likely that the exercise in the exam will be split up into small parts. Like I think some of the exercises in the course notes. If like a proof is very easy, we'll just say prove this theorem. Okay, so okay, I see a couple of calls for 6.36D. Let's do that one. That looks like a one that's more difficult. Yeah, so let's do that one. 6.36D. So we again have inside the sphere. Okay, this time we have a sphere with radius √2, and outside the cylinder. Okay, so let's make a picture again. Right, okay, I don't have to ask you what we always start by drawing a picture. So we have root 2, which is here somewhere. So. This should be a single point. Inside that sphere, this actually goes all the way around. So, okay, that is my impression of a sphere. Doesn't look that beautiful. So that's red. And then we have a cylinder. Okay, that's easy. X squared plus y squared is 1. So let's say this is 1. I'm not going to draw all the intersection points. Right, my sphere's radius root 2, so that will be root 2. And then, okay, so there's no z, so that thing is going to repeat over every z, so that's going to go up like this, right? And down. So it's going to hit this. Okay, so what is the question? Inside the sphere and outside the cylinder. Okay, so what do we see? Okay, let's do the same thing as before. So let me again use my different colors. So I've got my angle theta over here. I've got my angle rho over there with the positives, angle phi over there, and then the rho is the distance. Which color did I use for rho in the previous example? I think I used blue. Okay, let's use a different color because I already used blue for my cylinder. So rho is, let's do that over here. Yeah, let's draw a line like this. So this is gonna be the rho, that's gonna be the distance to the origin. Okay, what can we already see? So we should first do some, so this is difficult because it's not entirely clear what's going on. So let's look at some of these variables and see what we can already see. So first let's look at theta. I think this is the easiest thing because we see that this thing is, how shall I say this, radially symmetric, right? Doesn't matter what theta is, it's going to look the same in every direction. Namely, we start at the origin, and then we are inside the cylinder for some parts. Once we travel along a ray, and then we hit the boundary, and then we are going outside. Yeah, but this is the same in every direction theta. So what theta is doesn't really matter. We see that theta definitely goes from 0 to 2 pi, because it's the same in every direction. It is a little bit vague, but hopefully you agree with me that theta is from 0 to 2 pi because it's the same in every direction. Can I get some confirmation that you guys agree with me? Yes. Okay, that's good. Okay, so now we have see there's already a big difficulty with the radius rho, right? Because you see, let's say we are on the negative y-axis. Let me draw my variables. Let me name my variables y, z, and x. Let's say we are on the negative y-axis, then we go from 0 to 1, and then the rho will be from 1 to root 2, right? It's going to be this part. It will be root 2, Tess. It will be 1 from root 2. This is true on the y-axis. Yeah, no, if I go in this direction, right, I go from 1 to root 2, from the blue to the red. If I go in that direction, it will be also from 1 to root 2, from the blue to the red. But now there's a bit difficulty, because what if I go upwards somewhat? Well, let's say I'm going very close to this intersection point, so I go up this way. Now I see that for a very long time I'm still in the blue cylinder, and only in the very last part, very small part here over here, I'm going from the cylinder to the sphere. Yeah, so here it's going from 1 to root 2, and here the radius will be bigger, and then I will still end at root 2. So I see that this is very important. Yeah, there were some suggestions in the chat, but this is a very important thing that we should see, that it depends on how much I go up. If I go up a lot, then the lower bound for rho is going to be higher than 1, because the radius is going to be bigger than 1. And the upper bound will always be the same, right? Because I'm also always inside the sphere. So this is what I can say about the upper bound. Well, rho, so the upper bound is going to be √2, because that's when I hit the sphere, but the lower bound actually is a little bit of a question mark, because if I'm on the xy plane, if I'm on the y-axis, also the x-axis, it will be from 1, the lower bound will be 1, but if I go up a bit, the lower bound will be bigger, right? You can see that from the picture. The radius will be bigger once I hit the blue cylinder a little bit above the xy plane. So this question mark is going to depend on phi, and this is what makes this question a bit more difficult. So maybe let's first determine the bounds for phi. Yeah, see first let's see what the bounds for phi is, and then hopefully later on we should be able to find the bounds for rho. Okay, are you with me? Are you still with me? So let's do phi first. That would be my suggestion. Anyway, let's just do phi first, and then we see what we can do about rho. Okay, so how does it work for phi? Well, to get some intuition, let's think about what happens if we have phi is 0. Well, if phi is 0, then I'm going to be inside the cylinder all the way, but I need to be outside of the cylinder. So if phi is 0, this will not be in my range, because then I will be inside the cylinder all the time. And if phi is small, I'm going to have the same thing, right? I will be inside the cylinder and until I hit the boundary of the sphere. So I see for small phi, this should be not included in the range. And the same thing for big phi. If phi is pi, I'm going all the way down, which is still inside of the cylinder. That's not good, because the region is outside of the cylinder. Yeah, so phi is pi should also not be there. But you see, if phi decreases a little bit, until once I hit this point, then the phi suddenly become acceptable, because then I will be in this region over here where there will be some red stuff, which is not blue stuff. Let me say it like this. In other words, there will be some parts inside the sphere which are still outside of the blue thing. Yeah, so I can see that phi, there will be two boundary values. Maybe let's do that in yellow. Should be from here roughly, from this intersection point to that intersection point. Yeah, so in this range, maybe I should have done it with green. This is the range where phi lives. Because if phi is less than that, we will always be inside the cylinder, and if phi is bigger than that, we will be always inside the cylinder. Okay, so this is very important. So do you all see this, or is this a little bit iffy? Do you all agree with me that the phi range should be in this orange region? Can I get some yeses in the chat? Or maybe if it's not clear. Okay, Tess agrees, that's good. Another yes, more yeses. Okay. Lots of chat messages. Okay, I see lots of yeses. Okay, that's good. So now, as before, we want to compute the intersection points. And as before, we see that it doesn't really matter which direction theta we go to, right? Because again, it's all radially symmetric. So I could go in the ZY plane, or I could go in the ZX plane, or I could go in between. But you see, the intersection will be like a circle over here. The intersection of the blue and the red, the blue cylinder and the red sphere will be a circle. And that doesn't depend on theta, right? Because the angle on any point, so if I draw my yellow point, you see that the yellow intersection point should be on this circle. Okay, we will get to your answer in a second, Joshua. So it doesn't matter which direction I go to. So let's do it in the ZY plane. The reason that I do the ZY plane is because that is sort of the facing plane in my three-dimensional picture, right? I have the ZY plane over here, so it's a little bit easier to draw. But you can also do the ZX plane. So let me just do this in the ZY plane. ZY. Okay, so what I do, I take my red region and draw it in the ZY plane, just as before. So again, that's going to be a circle with radius √2. And the blue region, the cylinder. So what does the cylinder look like in the ZY plane? Well, these are just going to be straight lines. You can see that from the picture, right? The cylinder in the ZY plane, when x is 0, is going to be straight lines. Let's write down the formula. So here we have y squared plus z squared is 2. And let's do the blue. So I claim there will be lines. There will be lines like this. And what are the equation of the lines? Well, if x is 0, then we have y squared is 1. So in other words, y is plus or minus 1. And these are precisely the two lines that I drew. Yeah, 1 and minus 1. So you can see it from the picture and you can get it from the equations. So this is important. You can use both methods. And you see that both methods agree with each other, right? I can use the picture or the equations, and I should always get the same picture. Okay, let me know if there are any questions so far. So what I've just been talking about is, well, we here have our angle phi, and then we need to find the yellow intersection points, this, there, and there, right? So let's call this the angle phi min, and then this angle will be phi max. And as I've just explained, the angle should be from phi min to phi max. It's a little bit small. I've tried to write phi min and phi max there. So I need to compute the angles belonging to the two yellow points. Well, how do I do this? Well, again, I take both equations and I take them together. So if y squared plus z squared equals 2 and the equation y is 1. Yeah, I can also use minus 1, but let's use 1. Then if I take them together, I see that z squared equals 1. So z is plus or minus 1. Yeah. So this is the point 1, 1, and then this is the point minus 1, 1. Sorry, 1 minus 1 in the yz plane. So do you all agree with me? Is phi only on the positive axis? Phi goes from 0 to pi, if that's what you mean. I don't quite understand that comment. If you could elaborate, that would help. So again, just reiterating, phi goes from here until there, from the positive z-axis to the negative z-axis. In every direction, so like this, or like this, or like this, or like this, whatever. Okay. Well, okay, so what are the angles? Well, okay, that's easy, right? So I don't need to tell you that the angle belonging to these 2 points, or this angle is going to be pi over 4, and that angle is going to be 3 pi over 4. So the angle, how do we get phi's bounds? Well, okay, so we need the angle here in this picture from the positive z-axis to that. This is the point 1, 1, so it lies on the line y is x. So the angle is pi over 4 because it cuts the angle in half. If you don't want to use that, you can use formulas to compute this, like well, you should all know how to compute an angle. Okay, let me just do this very briefly. Just draw this gray triangle over here, and then compute this angle there, right? We know that this length is 1, this length is 1, and this length is √2. So you should all know how to compute the angle there. I will not go over that again. So this is the angle from the positive z-axis. So this is angle pi over 4, and this angle will be, by the same reason, will be 3 pi over 4. Yeah, so you can see from the picture that phi will be between pi over 4 and 3 pi over 4. Okay. Okay, let me again ask if there are any questions about the angle phi. Please show again where pi over 4 is. So pi over 4 is on this line. Sorry, z equals y. It's this direction. So in the 3D picture, pi over 4 would be like there, but in a whole circle, right? Because I could go in any direction. I could go like this. Could go like this. So in this picture, pi over 4, because I'm computing the angle from the positive z-axis, so from here to that yellow intersection point. So that will be pi over 4, right? Because from here to here is pi over 2. We know that, right? The entire circle is 2 pi, so this is a quarter of a circle that's pi over 2. So half of that is pi over 4. And if you don't see that, you can always draw the triangle like I did with the gray triangle. Does that make sense, Olivia? That this angle is pi over 4? Remember, we are always computing the angle with the positive z-axis. And then here it's the same, right? This angle will be this angle and this angle will both be pi over 4, and the entire thing will be pi. So it will be pi minus pi over 4, or you can do pi over 2 plus pi over 4. No matter what you do, you should always arrive at the angle 3 pi over 4 here. Okay, let me know if there are other questions. There's a question. Could we also use 1 is the rho cos phi to also find the angle? Yeah, because this is it's sort of like polar coordinates in the zy plane. That's how you can also think about this angle. But I think I strongly prefer this picture because that keeps track of me. So I would say actually no, sorry. Andre's question. I would say no, because phi is not the angle. Normally, if we have a plane like this, then phi, if you have polar coordinates, phi is the angle from the positive y-axis going up. But our angle phi is from the positive z-axis going down. So it's different. It's not really like polar coordinates. So I would just do. I think the way I do it is the clearest, because you see the important part is you need to understand what's going on, and we need to understand that the phi angle is from the positive z-axis, and therefore just use this picture. I would recommend that. Okay, now we need to think about rho. This is going to be a tricky situation, because as I mentioned before, this is going to depend on where we are. Okay, so now I'm going to have to think a little bit. So how do we compute rho? Okay, so the upper bound is clear. The upper bound is √2, and now the question is, how do we compute the lower bounds? And I want to use the same strategy as for polar coordinates, right? I will hit the cylinder first, and the cylinder has equation. So the blue equation. Okay, so now I want to compute the lower bound for rho, and my equation is like this. No, it is not 1, because, so as I tried, yeah, so this is a bit difficult. If I am on the y-axis, then it will be 1, right? Because then the radius 1, I will hit the cylinder, and that will be my lower bound. But if I go slightly up, I will hit the cylinder at a bigger radius. Rho is the distance to the origin, so that's not the radius of the cylinder. That's the distance to the origin. So if I go up, the distance will be bigger. Yeah, exactly. So what I do is I take the equation of my cylinder and then transform that in spherical coordinates. So I wrote the spherical coordinates in the previous exercise and not this one. So I'm gonna have to Miss Toya already gave the answer, but let's see if we can also derive this ourselves. Right? Let's recall what x is. X is rho cos theta sine phi, and y is rho sine theta sine phi. I will not. Okay, let's also write down what z is. I don't think I need it. Okay, so let's transform this equation, which is the equation of my cylinder, and that corresponds to the lower bound of my rho. This is why I'm working with this thing. It's the same if you have polar coordinates. Remember, if you have polar coordinates, you rewrite the equation of one of the bounds in polar coordinates, and that's how you get the bounds for your r usually. And here we have the same, but with rho instead of r. So we take the equation of the lower bound of rho, which is this, and we can see that from the picture. And then we rewrite it into polar coordinates. So let's do that. Okay, so x squared is going to be rho squared cos squared theta sine squared theta plus rho squared sine squared theta sine squared theta is 1. Okay, now I will leave this to you to see that I need a different color. That we have a cos squared and a sine squared, and the sum is 1. So this is going to be equivalent to the equation rho squared sine squared phi is 1. Let's see if that's the same as what's put in the chat. Yeah, rho squared sine squared phi. Yeah, just take out the cos squared and the sine squared, and they add up to 1, and therefore we will get this. Do you all agree with what I've done here so far? Yes, so that's good. Okay, and remember what we're trying to do is we're trying to find the lower bound for rho. So that means we have to take our equation and make rho the subject of the equation. Well, that's easy because we see that rho squared is 1 over sine squared, so rho is going to be 1 over sine phi. So that's going to be the lower bound. So that's going to be the lower bound. Yeah, so 1 over sine phi. Okay, just to see if it makes sense. If we're on the xy plane, so remember what I said before, if you're on the xy plane, for instance on the y-axis, then I said that the lower bound for rho would be 1. Let's see if we can verify this. What is the angle phi if we are on the xy plane? What angle phi corresponds to that? Can someone tell me that? What's the angle phi that corresponds to the xy plane? Or if I'm on the y-axis? Exactly, it's pi over 2. Remember, the angle phi is the angle from the positive z-axis. So if we're on the xy plane, anywhere on the xy plane, in particular on the y-axis, we have gone half of the way from the positive to the negative z-axis, and therefore the angle will be half of pi, which is pi over 2. Yeah? So if we're, let's do this as an aside. So this, what I'm doing now is not strictly necessary. I'm just trying to convince you that that this is the right bound. So if we're on the xy plane, in particular on the y-axis, we have that our angle is pi over 2. The sine of phi is then sine of pi over 2 is 1, and that means that 1 over sine phi is also 1, because 1 over 1 is 1. Yeah, so as we see, if we are actually on the xy plane, then the lower bound for rho is 1, and that's exactly what I said. I also said that if we're close to this angle, then the lower bound would be very close to root 2. Okay, that's a good question. The way we all mark is the ideas are the most important. Actually, I personally think that the computation is not that important. So if you just get one bound wrong, but the rest is fine, you will get the vast majority of the marks. Or if you make a calculation error. These things are not important. What's important is that you understand what's going on. I don't know. I want to make another general comment. These questions about marks are not very useful. What you should be worried about is how do I answer the question. Let us worry about the marks, okay? We will give you marks depending on how well you're able to answer the question. So your only goal should be to answer the question as good as possible. Okay. Now let's see if what happens. Remember, this boundary value was the angle pi over 4. So what happens if let's do that again as an aside. What happens if we're in if phi is pi over 4? Then the sine of phi, well, what's the sine of pi over 4? That's 1 over root 2. So that means that 1 over sine phi is going to be root 2. So we see if the angle is pi over 4, then the lower bound for rho is going to be root 2. So it will be from root 2 to root 2. So it will be nothing, right? It will be just a single point, but you always want like an interval. And that, if you look at our picture, this makes a lot of sense, because if I go to the yellow point, the blue cylinder and the red sphere are exactly equal. So rho will just be a single point. I will only hit outside that and inside that only on a single point. So hopefully you see that this thing actually makes sense, the 1 over sine phi. I've computed two angles, and for both of the angles it seems to be correct. Okay. I think for the rest of the exercise I don't have to do it, because now we have... Okay, so let's just write down the final bounds. Yeah, so we have phi is between pi over 4 and 3 pi over 4. Theta, as we discussed that already, was between 0 and 2 pi, and then the angle rho was between, sorry, the radius rho is between 2 pi and 1 over sine phi. And then you have to do the Jacobian and so on. But I think we can skip this unless there are any pressing questions about that, right? That is not the most difficult part of the exercise. Okay, are there any questions about this exercise? Then you have to rewrite the integrand, but it's z squared. Okay, but that's going to be rho squared cos squared phi, right? From that way. Okay, so are there any questions about this or any further questions about anything else? I want to refer to my previous answer. Johnny, your question is not relevant. Your job is just to answer the question as good as possible. Let us worry about the marks. Okay, there's another question. 6.3.7c. No. You can ask just questions about anything. Innocent. Maybe. Do you have a question about not chapter 6? But I would prefer to answer a question about a different section. Otherwise, it's going to be a little bit one-sided. Or do you not have a question? Then I will look at 6.3.7c. That's fine. Okay, I will clear the screen because I haven't had any question. Okay, I will just start with 6.3.7c, which is we have to calculate the volume. Okay, let me just skip this volume. I think this is not the difficult part. The difficult part is going to be the sketch. So it's going to be inside the square x squared plus y squared plus z squared is a squared. And then we have planes. Y is 0 and root 3y minus x is 0. Right? It says bounded by these two planes. Okay, let's try to go a little bit quicker. So how do we draw this? Well, I want to think about, we have our two planes. Well, these two planes do not depend on z, right? They have no z in them. So let's first sketch these two. Well, there will be lines in the xy. Let's first sketch them in the xy plane, and then we can put them in 3 dimensions. Especially this plane over here, right? So the second plane is, let's rewrite this a little bit in gray. Y is equal to x over root 3. Is that correct? I believe so. So let's for theta, usually it is clear from the sketch, so you do not have to make this clear if you say from the sketch, but if you just say, if you do not make a sketch and you just say theta is that, then it will not be accepted. It must either follow from computations, but I think it is almost always easier just to see it from the sketch. There must be some kind of explanation, but the sketch is usually good enough. Okay, y is x over root 3, so that is a line with a slope of 1 over root 3. And y is 0, well, that's the x-axis, right? Okay, so that was not so difficult. So let me now try to put this in 3D. What do we have? Y, x, z. Okay, so this line is, so this is the x-axis, that's the y-axis. So we have, let's see, y is, this should be x over root 3, apologies. So we have y is 0, so that's, okay, maybe I should use a different color. So let's do them in blue, the lines. So the line y is 0. Okay, this is a plane, but I'm just drawing in the xy plane now. It's going to be this. And the other line is like this, right? Okay, but these are planes, so the same for every z value. So I'm gonna get planes like this. So that's one of the blue planes, and the other plane is the same. It's gonna be like this. Okay, are there any questions about? I've drawn these two planes in 3D. Any questions about that, or wondering how I'm did? So basically, I got two. You can think of them as two pieces of paper that are upright that are cutting in the line in the z-axis. Right, they intersect in the z-axis. Let's draw this as well. Let's draw this in purple. Right, they intersect in the z-axis. Yeah, these are my two planes. Are you? Can I get some agreement in the chat that you are with me? Yes. Okay. Nicola says yes, and she asked the question. Hopefully the rest of you. Okay, and then of course I've got my sphere. Okay, now the thing is I don't know what the radius is. It's A. Is anything given by A? So A, let's assume A is positive. If I would make this question, I would say that A is positive. Because if A is negative, then it doesn't really make a lot of sense. So let's just say that A is positive, and we've got a. Just gonna draw the sphere as before. So I've got a sphere like this. Yeah. So I've got my sphere, and then I've chopped my. So think of my sphere as an onion or an apple or an orange, and then I chop through them from above with a cleaver in two slices. So what I'm gonna get is I'm gonna get two pieces. Yeah, so if I look at it from above, let's look at it from above. So what do we have? We have our red circle, and then I chop them with two blue slices, so a slice like this and a slice like that. Yeah, this is how it looks like from above. So this is important. I need to get a good picture how it looks from above. But note that this is not a pie, right? Because it's a sphere. So this is an orange. So I've taken orange and I'm chopping it up like this. It's a little bit weird, but okay, that's what I'm doing. Okay, please let me know if anything is unclear about this intuitive explanation so far. Okay, let's see, what does the question say? The question say bounded by these planes. So it must be inside the sphere and bounded by the planes. Oh, and it is in the first octant. That's something that I have not taken care of yet. So it must be in the first octant. This picture is actually a bit bad, so I'm gonna. Yeah. So again, let's look at this on the x. So let's cross out this picture. So again, let's look at the xy plane. Then I've got my red circle, and then I've got my two blue lines. So they are like this. Right? These are the lines that are already computed above. Okay. So I can see from okay, so it's in the first octant. So if I look at my 3D picture, so it must be bounded by these two planes, and it must be in the first octant. So I can see it's in this little slice over here, between that plane and that plane, and that corresponds to the first quadrant corresponds to this part over here, between these two lines. So this is where if I look at it from above, this is my orange slice, right? I'm slicing my orange. And this is the slice that I have to integrate above, because it's in the first octant, so that means x and y both have to be positive, and they have to be bounded by these two planes. So that's going to be this piece of the pie over there. Sorry, it's not a pie, this piece of the orange. Yeah, are there any questions about that? Okay, while you guys think, let me again draw my angle. So I've got my theta over here, I've got my rho, I've got my phi over there, and I've got my rho. Let's do that in purple. So it's going to be my distance. Let's say it's going to be like this. Yeah. Okay, so what should theta be? So what should be the bounds for theta? So if we look at this picture on the xy plane, we see that theta is this angle, right? Oh, wrong color. Should be orange. Yeah, so this is my theta, and I see that I must be inside the slice. So again, what I see is I should compute this intersection point, and then theta is going to be from there to there. Yeah, so let's compute the intersection point. Okay, let's do that in orange. Let's do that over here. So the intersection point, that's where. Okay, I should compute the angle. Okay, now it's a little bit difficult because my red sphere is in terms of A. But I should know how to compute the angle of the blue line, right? The blue line is a fixed angle. No, it doesn't matter where on the blue line I am, it will have a fixed angle. For instance, I could take x is 1 and then y is 1 over root 3. That's a possibility that I can do. So let's draw a triangle like this. So I can take any point on the line. For instance, I can take the point x is 1 and the y is 1 over root 3. And then I should figure out what is the angle theta over there. Okay, so that's gonna be, can use the tangent, for instance, tangent of theta. Yeah, let's use the tangent, that's the easiest. The tangent of theta is gonna be 1 over root 3, which implies that theta is pi over 6. Yeah, so do you agree that this angle theta over here is pi over 6? So this angle, this corresponds to this angle, theta is pi over 6. That's going to be that bound for the theta over there. That's going to be the upper bound. But I need my slice, so the lower bound for theta is going to be 0, because it's going to go from 0, the positive x-axis is 0, to pi over 6. Yeah, so theta is going to be from 0 to pi over 6. Okay, any questions about theta? Okay, so what about phi? So again, now it's helpful to picture the orange. Well, if I slice my orange from the top, remember we are in the first octant. So I only take, yeah, so the first octant is where z is also positive. So the phi that I should be taking is, I should take this slice, but I cannot go below because I'm in the first octant. Yeah, so this is also given in the question. The first octant is where x is positive, y is positive, and z is positive. And the z is positive, that corresponds exactly with phi between 0 and pi over 2, right? Because what we've already discussed a lot, if z becomes negative, that's where phi is bigger than pi over 2. And I can also see from my picture that yeah, so if I go inside of this slice of the orange, I immediately get a piece of the orange. So the phi starts really at 0 and it ends at pi over 2. Yeah, just if you don't see that, just take an orange yourself and chop it up like this, and you see that if I'm on the positive z-axis and a little bit further, I immediately hit my slice of orange. So it's going to be, the lower bound for phi is going to be 0. Okay. Now for rho, what about rho? Okay, so for rho we should just draw an arbitrary line and see if we can derive something from it. So let's do this purple line, or another purple line. It could also go like this to this point over there. We see that rho, no matter which direction I go, so the direction is determined by theta and phi, I always go from the origin to the boundary of the sphere, right? Because there are no other boundaries. The blue boundaries have already been taken care of by the angles. Yeah, the fact that we're in the first octant is taken care of in the angle phi. And the fact that we are in this slice here, that's taken care of with the angle theta. So for rho, we always have a full line segment from the origin to the boundary of the orange, and therefore rho is between 0 and the radius of the orange, which is a, because that is the equation of the orange. So I've got my 3. bounds over there. I think I will not do the question further because I think the rest is sort of standard. The Jacobian and so on. So are there any questions about this? Okay, I've got a question about question 5, but let me first ask if this explanation was clear and if there are any questions about this. Okay, I just want to iterate that these are difficult questions, and yes, you just have to see it. The only way is to see it. Okay, if there are no questions, let me clear the screen and let me continue with Mr. Shai's question about 5.6. I think that is about the transformation theorem. Okay, let me only do question 2. Okay, yeah, let me just give an indication for question 2 and then maybe try question 3 yourself. Let's just say 3 is not that important. So let's just do question 2. So I've got an ellipse. So the equation is x squared over a squared plus y squared over b squared is 1. Okay, we assume here that a and b are positive. The question is, how can we solve this with a transformation? So here the idea is we should think about polar coordinates, right? Normally we have polar coordinates, and then we say, well, what do we say in polar coordinates? X is r cos theta, and y is r sine theta. Yeah, that's polar. And then we can compute the area using polar coordinates. Now in this case, that's not very convenient because we don't know where 1 is. If we take x and y like this, then then I'm gonna go over some kind of circle, but I don't want to go over the circle, I want to go over the ellipse. So the trick here is, but let's just change polar coordinates a little bit, so that instead of polar coordinates, we're gonna use ellipsoid coordinates. Let's call them like this. Well, how do we do this? Well, what I want is that, well, I still want my r from 0 to 1, and my theta from 0 to 2 pi. So let's take x equal to a r cos theta, and y equal to b r sine theta. So try this, and now try to see yourself that if you do it like this, then if r, okay, so r is no longer the radius because these are ellipsoid coordinates, but check yourself that if r is from 0 to 1 and theta is from 0 to 2 pi, that then the xy, the vectors xy, they will be exactly the ellipse. So they will exactly go inside the ellipse. So this means that my region over here, which is an ellipse, can be, with this transformation, which looks very similar to polar coordinates, but is slightly different, transforms into a rectangle on the r theta plane. So now theta is not exactly the angle between the positive x-axis, and r is not exactly the radius. They've been modified a little bit, but you can check yourself that if you take these variables like this, that then x and y actually becomes this ellipse. So think of this in generalized polar coordinates or ellipsoid coordinates, and then you get exactly your ellipse. Now, to solve the question further, you just have to think about how to compute the Jacobian here, because we know that the Jacobian for polar coordinates is r. The Jacobian for this transformation is going to be a little bit different because there's some extra constants. Yeah, but if you do this, you should be able to get the answer pi AB. Yeah, I don't think I will fully explain the whole exercise, but this is roughly the idea. I recommend that you try this yourself. Okay, any questions about this exercise, Mr. Shai? Yeah, Okay, the difficulty of this exercise is that you have to sort of you have some intuition about polar coordinates and see, oh, if I change them a little bit, I will get something that I could conceivably call ellipsoid coordinates. Be careful. It's yeah. So r is no longer the radius. You see, because there's an extra factor a here. So what I'm doing, I'm sort of stretching my x-coordinates. Normally we have a circle. Let's draw a circle in red. Let's say that a and b are bigger than 1. Normally I have a circle, but by introducing this extra coordinate r, this extra factor a, I'm sort of stretching this part of the circle. So it becomes like this, right? If I would take b as 1, by adding this extra factor a, I will not get a circle. I'm going to stretch my circle, so I don't get a circle. And then similar for b, let's do that in green. Because of this extra factor b, I now take my ellipsoid and I also stretch it upward because I multiply my y with b. So this is assuming that b and a are strictly bigger than 1. But it will also work for less than 1. But that is something that you should verify. So verify that if you're inside the ellipse, so the ellipse has this equation, right? Inside the ellipse, it's less or equal than 1. This is going to be equivalent to saying that these two things are true. But now r and theta are not polar coordinates, they are ellipsoid coordinates. So please verify this statement over here that these two things are equivalent, right? And remember, I can rewrite this in terms of x and y, or I can take this equation and plug in what x and y are and then compute what I get over here. And then I see that this ellipsoid in the xy plane gets transferred into a rectangle on the r theta plane. Okay, but you just have to do it, so maybe I will just recommend that you try it. Okay, any further questions about this? Okay, I don't want to do this fully because yeah, question 3, let's just maybe skip question 3. That's a little bit complicated, more complicated. So just skip question 3. If you can do question 2, that's good enough. There was another question about an outline of the proof for theorem 42.7. Well, that is in the course notes. This is by Miss Ramatuba. This is in the course notes. So I don't think I should do that. If you have some questions about the ID in the course notes, I can answer that, but okay. Okay, are there any further questions? Oh, we're already been quite a long session. Let me get a cup of tea. I'll be back in a minute and then I see if there are more questions. Yes, the 1.5 hour of session is thirsty work. Let's put it like this. Do we have to know the proofs of the theorems that are given in the exercises? Yes, except for those that are not examinable. It seems that there are no further questions, so okay, let me stop the recording.